All right, and now it's time to continue our journey towards non-zero temperature lattice QCD. And this we'll do in steps by first reminding some general concepts and then going over to scalar field theories, eventually to Young-Mills and full QCD. So we are at this stage in the plan of our course, so in the theory part of the non-zero temperature QCD. Let's then review some known facts from statistical mechanics. We know that any thermodynamic equilibrium property can be obtained by taking derivatives of the partition function, which is written as the trace of the negative exponential of the Hamiltonian, which in front has the inverse temperature written as beta. And at that point, we can already start taking derivatives. If we take derivatives of the logarithm of the partition function against beta, we get up to a volume factor the energy density, or we can get the pressure with the volume derivative, or we can get densities taking derivatives against the chemical potentials in a grand canonical picture, or we can get the entropy density by taking thermal derivatives with some volume factors. Please keep in mind that I'm using small letters for intensive quantities and capital letters for extensive quantities throughout the class. And then we know also how to express thermodynamic potentials, such as the internal energy, in terms of all relevant thermodynamic variables and observables. The same thing we can do by taking twice derivatives against the thermodynamic variables, which gives us the response of our thermodynamic quantities, such as the pressure or the densities, to changes in some thermodynamic parameters. These are also called generalized susceptibilities and give us a measure of the fluctuations in our system. As we have argued about the importance of the partition function, because we can obtain thermodynamic observables by taking derivatives of the partition function, we continue discussing the partition function because it is interesting to see that when we write the partition function as the exponential of minus beta the Hamiltonian, actually the partition function resembles pretty much to the quantum mechanical evolution operator, but with some change, in particular with the change that we move to imaginary time. So t goes to I beta, and thus there is this correspondence between the evolution operator in quantum mechanics in imaginary time and the partition function that we have just written. So thus the evolution operator is replaced exactly as I wrote on the slide. In quantum mechanics, we also learn how to tackle time-dependent problems by splitting the Hamiltonian of the system into a time-dependent and a time-independent part. And if at that point there are circumstances that ensures us that we can treat the time-dependent part as a perturbation, so that it is negligible with respect to the time-independent part, then we move to the interaction representation, where we can write this perturbation in this form. And at that point, we have that we can write the transfer matrix accordingly, which leaves us with an expression for the partition function in terms of the corresponding Z0 partition function for the unperturbed system. And then we are in a position to measure any expectation value of any given observable just according to this expression that I wrote on the slide. And in the path integral quantization formalism, you learn yet another way of expressing the partition function, as you do when you study, for example, a particle in one dimension, which is subject to a potential V as a function of its position Q, and you want to write the matrix element of the evolution operator, as I did on this slide. Then you learn that under a weak rotation and under compactification, to take the trace, you obtain yet another expression for the partition function, which looks like the expression I have on this slide. And now we should be ready to move on to field theory and take our first step in field theory by considering a real scalar field theory written in a Euclidean path integral formalism. Here I have the Lagrangian of such a field theory. And now what happens is that in a non-zero temperature setup, we would integrate the negative exponential of the action over all fields under appropriate boundary conditions for the fields, which in this case are scalar bosonic fields, so they are subject to periodic boundary conditions, as this is important to ensure the statistics properties of bosonic particles. And then this is the expression for the partition function in our scalar field theory, and there are at least two important remarks in order. The first one is that if you take the t to infinity limit, which is the same as sending beta to 0, we see that the tau dependence, the weak or imaginary temporal dependence of our expression completely cancels out. It plays no role, and you are left with this other expression for the partition function, and this is telling you that basically you have a three-dimensional reduction of your theory. And second important remark, which as I already stressed has to do with the periodic boundary conditions, is that you want to make sure you implement for scalar bosonic fields periodic boundary conditions, and for fermionic fields, if there were in our theory, antiperiodic boundary conditions with the same period. Okay, and then staying in the context of our scalar field theory, we can also take a look at the propagator, which is defined by the fact that it is the solution to the Green's equation, which I have written down that you can read on the slides. It is particularly informative to look at the zero momentum projected Fourier representation of the propagator, because this is written in terms of the so-called Matsubara frequencies, now that we have compactified the temporal directions, and in terms of the propagator in the transformed space, of course. In simple cases, like the ones which is also explicitly given here, in simple cases like the one that we have at hand, we can even perform the sum over Matsubara frequencies explicitly, and we obtain an expression for the propagator in terms of the Bose-Einstein distribution. Okay, with that in mind, let us move on to the pressure in the case of the scalar field theory, and in particular to an attempt at determining it perturbatively, to see how reliable a result we can get at some given order in perturbation theory or in the weak coupling expansion. In particular, now we consider the lambda phi to the 4 theory, and there are results in the literature for the weak coupling expansion of the pressure to order lambda to the power of 5 half, which is g to the power of 5. And of course, there is a prefactor, P0, which is the what you would get for an ideal boson gas. And then you have the perturbative expansion, and g square is the ms bar coupling constant at some renormalization scale, which we dubbed mu bar. What can we say about this weak coupling expansion of the temperature? First of all, that there is some poor convergence in perturbation theory, and secondly, there are further reasons for concern that I would like to comment by showing you this figure, where you can see some bands. The fact that we have bands depends on the fact that a range of mu bar has been considered at any given order in the expansion. And the first remark you can make by looking at G with powers higher than 2, so at these 3 bands, is that nevertheless the expansion seems to be unreliable as soon as mu is made larger than 0.4. Moreover, we see that this expansion is not really satisfactory in the sense that it contains non-analytic terms like these powers of the coupling lambda and logarithms. These result from infinite resummation of subsets of diagrams in perturbation theory, and of course are another reason for concern about this perturbative expansion of the pressure. We can move on and look at the perturbative expansion also of the Debye masses, which are defined as the pole of the Euclidean propagator. Therefore, they satisfy this equation. And what you obtain is that In the massless case, the weak coupling expansion for the square of the Debye mass, which we will look at even at a later stage when we will discuss the phenomenon of screening, if you are wondering or if you are unaware of what the Debye mass represents physically. For the moment, just look at the expansion, which is reported on the slide. And again, poor convergence and reasons for concern. Keep in mind that in the figure which I have on these slides, the masses are normalized to GT, which is basically the way that MD enters at leading order in the expansion. You again have bands because different mu bar in a range have been considered, and you observe a very large sensitivity at OG square, where you have a rather large band, especially towards larger value on the x-axis. And on top of that, there are large differences comparing the g square to the g to the power of 3, and therefore this is not a reliable estimation at that point. And that's the bad news. If you move from scalar fields to non-abelian gauge theories, it only gets worse, in the sense that we can see, and we will see it in the next two slides, that at non-zero temperature, perturbation theory breaks down in this case, in particular due to severe infrared divergences, which come from the so-called Linde problem. What is that supposed to mean? That if you consider the gauge field propagator this time, where the subscript E stands for electric, and you extract or try to extract the corresponding electric screening mass, which is the counterpart of the Debye mass that we have just discussed in the scalar field theory, and is a footprint of the fact that the color electric field is exponentially screened in a thermal plasma, a phenomenon that we will discuss again later on. You see that there are, first of all, issues with the definition themselves of these Debye masses. And where do they come from? They come from the fact that if you split the propagator into a vacuum contribution and thermal contributions, you find out that there are no new divergences coming from extending the formalism to a non-zero temperature, which is of course good news. However, we have that the infrared behavior is changed dramatically due to the thermal contributions. In particular, if you expand the Bose-Einstein distribution in the expression for the propagator for kappa values which are significantly smaller than the temperature, you see that there is a leading term which goes like an inverse power of k. And the result of that is that the electric screening or Debye mass becomes ambiguous already at higher orders in perturbation theory from next to leading order. And when it comes to the magnetic screening mass, it gets even worse, in a sense that I clarify in the next slide. The problem is that in thermal QCD, in perturbation theory, you have dynamical generation of, for example, the electric Debye mass. So originally, massless gluons acquire effective perturbative masses, which are generated dynamically by loop corrections to the propagators. And these dynamical masses are very important because they regulate the convergence of the perturbative series. However, color electric screening masses appears at order GT, and color magnetic screening masses do not exist perturbatively. Then they are introduced effectively, and at that point they enters like G to the power of 2 times T. With the above masses, the perturbative series, for example, for the pressure, stops being defined at order G square. Why? Because the gauge coupling drops out of the effective dimensionless expansion parameter completely at this point. And when that happens, you suddenly are having a term where there is no G dependence, and then all higher loop orders will contribute to that order. And long story short, because this is a rather intricate issue and we don't enter into the details, if you want, you can look at the original papers. The perturbative theory only works up to some observable dependent finite order, and then breaks down. I apologize for this small t, which should have been a capital T. And with that, I want to wrap this video up by saying that we need to tackle issues in QCD thermodynamics by means of non-perturbative tools for the reasons that we have just looked at. That screening masses, as well as many other phenomenologically relevant quantities in QCD thermodynamics, have by now been investigated and computed in lattice QCD simulations. And we will spend the rest of the class, at least for the non-zero temperature part, going through some of these calculations and some of these applications.